Okay, so up until this point, we've been looking at some of our exponential equations, and basically we've been given what our base is, and for whatever amount of time, we talk months, years, minutes, we've been given this value saying like, okay, maybe it's 12 months. And maybe if you're doubling something, you're timesing it by 2, and maybe the initial value was 100. And we've been solving for, you know, kind of what would be the result. Or sometimes we solve for our initial value. What if I wanted to give you guys a scenario in which I wanted to know how many times something needs to be doubled in order to get a certain number, right? Basically, what are we going to do when we want to solve for the exponent? Okay, now this is where logarithms come into play. Now logarithms are pretty cool. A lot of times they're just presented to students kind of, okay, here are the rules, here's what it is, go ahead and use it and solve for it. But the fact of the matter is there was this guy Napier, who before computers kind of came up with this computing system of Napier, they're called Napier's bones. And he was able, in the 1500s, without a refrigerator, a car, a satellite, a light bulb, I don't even know what they use for pens, maybe just with a feather pen, was able to come up using trig, sine of a theta, and it's called, like, he would call them particles, and he was able to relate trig to kind of this idea of like, if the value of sine is moving, the logarithm is going to, the distance is just going to be a little bit more. So he created this thing in the 1500s, which basically ended up turning into what we call a logarithm, which essentially is like this idea of two things, the product of two items as a logarithm are the sum of those two logs. Right? Just now, we are not going to go back to the 1500s and investigate what he was doing, because that would take a month or so to create a logarithm. But just this idea of, okay, what is this log I'm working with? I think it's better to just understand that how it was created in a sense, and it's a relation, meaning something was found where the change in one caused a change in another, and that relation created basically like this computation that you could make. That's why it's on your calculator. It's a log. Okay, this log. When you punch in log on your calculator, basically this thing created in the 1500s is being computed. Okay. Now we have a base raised to a power equal to an output, right? Now, in the past, if we wanted to solve, let's say we had y is equal to x plus 10, okay? If we wanted to solve for a different value, we would do what? We would use the inverse, right? We would say, okay, I want to solve for x, subtract 10, x is equal to y minus 10. And if you graph that, and you said, okay, start at 10, here's 10, I'm going up 1 over 1, and then here's its inverse, you're at 10, or 10 here, and you're going, here's your inverse, right? So we're talking about inverse. So if we want to solve for an exponent, we're gonna use an inverse. Now the inverse of a base raised to an exponent is a logarithm. So basically what you're saying is, okay, log of my base will give me a value of y. So basically, what is the value? What do I need to raise this base to get this value? So if I want to get x by itself with a base and an exponent, I have to take a logarithm. Okay, I can't just move pieces around. In order to separate this exponent from the base, I have to use a logarithm. So let's say I had a simple case like 2 to the x is equal to 8. Now mental math, you can solve for this. You know 2 to the third is equal to 8. Okay, but if we're to solve for this in other cases where mental math is not included, we still have to start incorporating a logarithm. So, and basically if I want to solve for x, log of a base of 2 will be 8 if it's raised to this power. Okay? Now if I want to solve for this, one way to do that is to change this into a base 10. So a common logarithm, if you see just log to the fifth, log 5 here with no base, you're basically saying it has a base of 10, common logarithm. What is our number system? And it's in 10. So this is basically putting a logarithm in our base of 10s. I could say x is equal to log 8. This is something I would put on a calculator. I would have to do over log 2. And if you put that on a TI, Texas Instrument, or any calculator, it's going to be 3. Log 8 over log 2 is 3. Now basically what ends up happening is you'll get 4 to the x is equal to 8. Now 4 raised to what power is 8? Well, we don't really know, right? Because it's 4 squared is 16. Don't make the mistake of saying this is 4 to the second power. So what I could do is take an inverse. Now you'll get used to the pattern. Basically log 4. Basically you're just switching the x and the y. This is your y here. So it just becomes basically log 4. It looks like it's raised to a power of 8, but it's not. Log 4, log base 4 of 8 is equal to what? And then what I can do is, if I want to solve for that, log 8 over log 4, and then I can get 1.5.
So the base is still the same, so you keep the 4, are you doing the switching the 8 and x?
That's it, yeah. It goes basically log base to your value is equal to whatever your exponent was.
Okay.
I like this. If you don't work with logarithms for a couple weeks, even, you kind of like have to go back and look at this. So I definitely like the use of this here. Now there are a lot of rules, like product, quotient. I don't even know if I know how to spell that. I think that's good. That will go over, etc. etc. That will go over. That will actually help you maybe get to this. But application-wise, this is pretty powerful, because when we were working on that bounce question, and we said that the ball bounces at 35 feet, and after each bounce it has about 3/8 of its height, and that's raised to what power? You could use a logarithm and actually solve for what this is. Like you can use this and then solve for what x is. So that's a good, because basically you'll have log of 3/8, and you wanted it to be 0.5, right? So basically in this 35 log to the 3/8 will give me a value of 0.5, and then you're able to